All right, students, we're going to do some work with simplifying roots. So I want you to have paper or pencil, write this down, all that jazz. Let's say I had the square root of 25. What does that equal? It equals 5. Good job, class. All right, what if I had the square root of, I don't know, 16? 4. Easy peasy lemon squeezy. What if I had the square root of 121? Maybe this one makes you stop and think, but it's just 11. Now, we learned this, I don't know when you learned this, 7th grade, 8th grade, 6th grade? Good for you. Let's dive into something a little bit trickier. What if we have the square root of 12 and we're trying to reduce that? Well, we're going to think about 12. We're going to break up 12. The math word for this is actually decompose 12, and we're going to decompose it so that it is factors. So maybe you are looking for perfect square factors and you're like, oh, well, 4 times 3, and that's the same as the square root of 4 times the square root of 3, and the square root of 4 is 2, so I'll get 2 root 3. If you did that, good for you. Maybe you didn't see that initially, and so instead you're thinking about 12, and you're thinking, well, what multiplies to make 12? Maybe you saw 2 and 6. Well, 6 can be broken down further. It's a composite number, and so you'll say, well, that's 2 times 3. And then you circle your primes and you say, okay, well, the square root of 12 is going to be the square root of 2 times 2 times 3. And since we're talking about square roots, we're looking for pairs of numbers. And so we'll go, oh, well, that's 2 squared. So we would have 2 squared times 3, the square root of that, which would give us, what do you think, 2 root 3. Now, either approach is fine. If you happen to see the perfect square first, then it's a little bit faster, but it's no problem to break it down. Let's try another one. How about the square root of 72? Try and do that one on your own. Pause the video. Don't cheat. Actually pause it and do it. Okay, we're back, and we're back. That means you actually did this problem. So if you noticed, 2 different ways to do this. If you noticed that 72 was 36 times 2, then lucky you, you quickly saw that this was 6 root 2. But maybe you didn't. Maybe you looked at the factors of 72 and said, well, that's 8 times 9. Okay, well, let's keep going because 8 is composite. That's 2 times 4, and 4 is 2 times 2, and 9 is 3 times 3. And so when we look at all of the numbers, all of those prime numbers, we find that the square root of 72 is equal to 2 times 2 times 2 times 3 times 3. And that is 2 squared times 2 times 3 squared. And when we take the square root of 2 squared, we get 2. And when we take the square root of 3 squared, we get 3. And we're left, poor little 2 is just left by itself, 2. And perhaps we notice that 2 times 3 is 6, and we get 6 root 2. Ta-da! It's the same. Go us. So we hope that you come to this class with this knowledge. Now for the new stuff. Let's say we had something like the square root of negative 25. Now, we know that 25 is a perfect square, but negative 25 is not. No number times itself equals negative 25. In fact, no number times itself equals a negative at all. That's just preposterous. But there is sort of like a 5-ness to this problem. So what if we could say that, could we like imagine a world where we could take the square root of a negative number? And that's what some mathematicians did. They just said, well, yeah, this is just like 5 false, 5 imaginary. I think they actually called them false numbers to start. So let's call this 5i, and let's call the square root of negative 16, let's call that 4i. And heck, let's call the square root of negative 121 11i. And as they're patterning and as they're thinking this through, they get to the essence, the square root of negative 1. The square root of negative 1 is I. And so when we think about imaginary numbers, the definition of an imaginary number is I is equal to the square root of negative 1. And so now when we see this, this opens up a world of possibilities. And if you're like, really, a world of possibilities? Yes, actually. So some of this stuff, this math was discovered hundreds of years before they actually discovered, should I say discovered, invented, before they actually discovered electrical engineering. And there's applications of imaginary numbers in electrical engineering. What? Okay, so let's say we're here. If I want to do the square root of negative 12, we did that earlier. Let's. So the square root of negative 12, we know that that is, when we think about 12, that's negative 1 times 4 times 3. Oh, 1 for 3. I love you guys. And the square root of negative 1, we said, was I. And the square root of 4, we said, was 2. And the square root of 3, oh, poor square root of 3, cannot be simplified. 2 root 3. 2i root 3. So now the square root of negative 12 is 2i root 3. And if we did the square root of negative, say, 75, pause, do, come back. You're back. That means you paused, you did, and you have an answer. Here's the way I think about it. I think about it as negative 1 times 25 times 3. 25 is a perfect square. So I'd have the square root of negative 1 times the square root of 25 times the square root of 3. The square root of 1 is I. The square root of 25 is 5. Oh, root 3. There we go. Aren't imaginary numbers fun?